Hello and welcome to the fourth and final video of the M3 chapter Elastic Strings and Springs. Quick starter question here. Write down the expression used to calculate the elastic potential energy of an elastic spring or string. This is the expression we had in the previous video, and I hope you remember that elastic potential energy is lambda x squared over 2L, where L is the natural length, lambda is the modulus of elasticity, and x is the extension. Together with gravitational potential energy and kinetic energy, we'll be using this expression in this video in order to solve energy problems involving conservation of mechanical energy. This is the new part to that, but most of this we've done in M2. So in M2 we worked with the principle of conservation of mechanical energy. In M3 we need to include elastic potential energy as one of the three elements. Remember, when no external forces are acting, the sum of the energy in the system, previously that was gravitational potential energy and kinetic energy, now it's also elastic potential energy, the sum of those three must remain constant if there are no external forces acting. So if energy in one form decreases, energy in one of the other form or forms must increase by that same total amount. So we had kinetic energy plus gravitational potential energy is equal to a constant in M2, now it's elastic potential energy as well. However, if external forces are acting, then the sum of the energy might increase or decrease when the work is done. So if work is done to put energy into the system, then this value will increase. If work is done against, say, friction or other resistive forces, then the total energy in the system might decrease. And I might write that as starting energy plus energy in from work done by external forces adding energy into the system, like a push or a pull, minus energy taken out of the system by doing work against resistive forces like friction, and that will equal the final energy in the system, where the starting energy and the final energy will each be made up of these three elements. So not much new here. We're going to jump straight into some examples and then finish with a few exam questions. First example, a light elastic string of natural length 1.6 and lambda 10 has one end fixed at a point A on a smooth horizontal table, so no friction in this example, and it's nice and horizontal. A particle of mass 2 kilograms is attached to the other end of the string. The particle is held at the point A, so the string is fixed at A and the particle is held at A as well, and then it's projected horizontally along the table with speed 2 meters per second. Find how far it travels before first coming to instantaneous rest. So initially it's traveling with 2 meters per second for a while because the table is smooth and the string does not stretch until it hits its natural length. When it hits that natural length, the elastic string will then start to stretch and slow the particle down. It will come to an instantaneous rest, say here, if I put that in blue, and then presumably it will bounce back because it won't be held in equilibrium here. There'll be no force pulling it this way at that point, but there will be an elastic force pulling it back this way. But we don't need to worry about what happens after this, we just need to find how far it goes before it gets to this point and gets to instantaneous rest, which means here the velocity will be 0. On the surface, a few of these problems look like you might be able to use kinematics, constant acceleration, things like that, but remember, as we slow down here, when the string starts to stretch, as the extension increases, the force increases. That's a variable force, which means it's a variable acceleration. And at this point here, this is not A equals 0, it is V equals 0. The acceleration at this point is negative, it's already slowing down, it's trying to pull it back this way. So although some of them look like kinematics might work, you'll quickly find you won't have enough information to solve them. Energy is what we're doing here. So in red, the starting energy at A, we've got gravitational potential energy, kinetic energy, elastic potential energy, and then the total. In this case, it's all happening on one horizontal level, h equals 0, so the gravitational potential energy will be 0 at both. If I call this B, That has not changed. We also know at B the velocity is 0, so the kinetic energy is 0. At A the kinetic energy is not 0, it's a half times the mass, which is 2, times the speed squared, and that gives us a total of 4. And here the elastic potential energy is 0 because it's a string which is slack, so there's no extension. At B there is an extension, but we don't know what that is. We know the expression though is lambda x squared over 2L, where lambda is 10 and L is 1.6. So we don't know the total at B yet because we don't know x. We do know the total at A is 4. So via this route here, we do know the total at B as well because there's no friction taking energy out of the system. There's no push or pull force adding energy into the system. So the 4 joules of energy here must all still be here at point B. So we know the total must be 4 because it doesn't change. That means 0 plus 0 plus this expression equals 4. So we get 10x squared over 3.2 is equal to 4. That gives us an answer of x as 4 root 2 over 5. Now let's think about what the question is actually asking. Find how far it travels before first coming to instantaneous rest. So it's from A to B, not just the extension. We need to also include here the natural length 1.6. So A to B is what we're being asked to find, and that is 1.6 plus x, and in decimal form that's 1.13, so adding 1.6 to that we get 2.73 meters, and that's 3 significant figures. Example number 2. A particle of mass 0.5 kilograms is attached to one end of an elastic string, natural length 2, lambda 19.6. The other end is attached to a point O, the particle is released from point O, find the greatest distance it will reach below O. So this is actually fairly similar, except it's happening vertically. O here, the particle is released from this point, and it drops down. When it drops, it then hits its natural length and stretches the string slightly, and then comes to instantaneous rest, before presumably bouncing back up a little bit. We want to find the greatest distance, so all the way from O down to here. We're doing a very similar thing here. At O, we've got gravitational potential energy, kinetic energy, and elastic potential energy to consider, to find the total. And then at the other part, which I'll name in a moment, we've got the same things, GPE, KE, and EPE, to give the same total because there are no external forces acting, only gravity. At O, to make the GPE easier, I'm going to make this my h equals 0 level. So that will be 0. It's held at rest, initially drops from rest, so that also is 0. And the elastic potential energy is 0 because the string has no extension. So the total energy in the system is 0. Now don't worry about that, because as it drops, remember relative to this point, the gravitational potential energy will become negative, and so the elastic potential energy can be positive to give a total of 0 there. It might look a little bit funny, but that's just because of how I've chosen my h equals 0 level. So if this is height equals 0, relative to that, this is the natural length of the string plus its extension. However, this is happening below the 0 point, so this is negative natural length plus extension, and that is negative 2 plus x. So be careful with your negatives on the gravitational potential energy, and I'll use that to call this point h equals minus 2 minus x. So the gravitational potential energy here is mass 0.5 times 9.8 times the height minus 2 minus x. The kinetic energy at the greatest point, as it stretches to its maximum stretch here and is about to come back up, that gives V is equal to 0. So the kinetic energy here will be 0 because we're at the greatest distance. The elastic potential energy, lambda x squared over 2L, And if we put lambda as 19.6 and L is 2 into that expression, we get 4.9x squared. But the total must remain 0 because there are no external forces. So this plus this plus this must equal 0. That gives me my equation of minus 9.8 minus 4.9x plus 4.9x squared must equal 0. Dividing everything there by 4.9 gives me x squared minus x minus 2 equals 0. Nice and easy to factorize to give answers x equals 2 and x equals minus 1. Now in this case, because it's a string, we can't have a negative extension for a string. So we can discard this answer and give this as our extension. Returning to the question then, to make sure we answer exactly what it's asking, the greatest distance below O is the natural length plus the extension. The natural length is 2, the extension is 2, so the final answer, the distance, is 2 plus x, 4 meters below O. Example number 3. A light elastic spring of natural length 1 meter, lambda 10, has one end attached to a fixed point. Particle of mass 2 kilograms attached to the other end of the spring, held at a point 0.8 meters vertically below A. Now be careful here. This is less than the natural length, but it is a spring, not a string. So this is compression. There will be elastic potential energy at the start. The particle is projected vertically downwards with speed this. Find the distance it travels before first coming to rest. So at the start, we've got a fixed point here, A, with the spring slightly compressed and a particle on the end of it. This is 0.8 meters, and it's projected downwards with a speed 2 meters per second. This is point B. So if it starts at B and is projected downwards, and there's a little bit of thrust in the spring pushing it down anyway, it's going to go down here, it's going to stretch out, and eventually it will hit a point where it comes to rest before bouncing back up a little bit. So it's that point there where it first comes to rest that we need to find. So the spring stretches out a little bit, and the particle is down here. Let me call this point C, and at this point V is equal to 0. So at point B, we've got gravitational potential energy, and if I make A my h equals 0 point, then that is equal to mass times 9.8 times minus 0.8, again because we're going below the 0 level, 0.8 meters. We also have kinetic energy, that is a half times the mass times the speed squared, and that's 4. We also have elastic potential energy because of the thrust in the slightly compressed spring. That's lambda times the extension, or the compression in this case, which is 0.2, square that, 2 times the natural length, which is 1. Gravitational potential energy gives me minus 15.68, and the elastic potential energy is very small at just 0.2, to give a total amount of energy in the system at the start of minus 11.48. Now that might seem strange having a negative energy in the system, but don't worry about that, it's just because I've used this point here as my 0 level, so all the gravitational potential energy is happening below that, so that will all be negative. At C, then, we've got GPE, mass times 9.8 times the height. Now we need to consider the height here. All the way down here, we've got the natural length of the spring, which is 1, plus the extension. And although I didn't put the negative on there, which I should have done, this also is negative. So we've got minus 1 minus x here for the height. The kinetic energy here is 0 because the speed is 0. And the elastic potential energy is equal to lambda times x squared, which we don't know yet, divided by 2 times 1. So that gives us 5x squared. And because there are no external forces in this example, the total energy must remain constant from point B at minus 11.48. Now we can form our equation. This plus this plus this must equal this, giving us minus 19.6 minus 19.6x plus 5x squared is equal to minus 11.48. And you should go through the process and show how you're solving that, but to save time on the video here, I'll just do that on my calculator. And that gives me the answer 4.297 ... or minus 0.377 ... Now again, we need to stop and think here, because this one actually could be one of the answers. We can have a negative extension on a spring, that's the compression. But given the context, starting here, which is at a 0.2 compression, less than this, and going downwards when it first comes to rest, it can't possibly have this extension. So just from the context of the question, we can discard this one. This must be the extension when it first comes to rest. But that's not what we're being asked to find. What we're being asked to find is the distance it travels. So it's got the extension, but it's also got a 0.2 meters worth of compression first before it starts extending. So the total distance from B to C is this extension plus 0.2 meters from the initial compression. So our distance B to C is equal to 4.297 ... plus the 0.2 meters from the compression to give a final answer rounded to three significant figures of 4.50 meters. Fourth and final textbook example before we do some exam questions. A light elastic spring of natural length this, modulus of elasticity this, has one end attached to point A on a rough horizontal plane. So although we're on a horizontal plane, this is slightly different because it's rough. We have friction. The other end is attached to a particle P of mass this, and the coefficient of friction is this. Initially it lies on the plane with this. Okay, I need to start drawing some stuff, otherwise I'm going to get lost. Point A here, and it's a spring, not a string. I'll draw it like this. Particle here at P. We need friction, so I'm also going to add on the weight here, 0.8 g, to give us the reaction of 0.8 g, because we'll need that for the friction. We're told that the particle lies on the plane with AP 0.5 initially, which is nice because 0.5 is the natural length of the spring, so initially there is no extension or compression, and therefore no elastic potential energy. Okay, back to the question. It is then projected with speed 2 meters a second away from A along the plane. So it's being projected this way with 2 meters per second. Find the distance moved by P before it first comes to rest. So as it comes along, the spring stretches and eventually it comes to rest, let's say here, with an extension, this, and that is also the distance travelled, so that's the amount we want as our final answer. Okay, that's a lot of information, but our method of approach is still very similar. We need to find the amount of energy in the system at the start, take away the energy lost to friction, which is force times distance, the work done against friction. So we need friction times it by this, and when we've subtracted that from the total energy at the start, that will tell us the energy at the end. So the energy at the start, we have gravitational potential energy. This is all happening on a horizontal level, so that is 0. Kinetic energy, a half times the mass times the speed squared, is 1.6. And the elastic potential energy, because it's exactly at its natural length, is 0. So the total at the start is just 1.6 joules of energy. But then we lose energy due to friction. The friction, because it's moving, is equal to, not less than, mu times r. Mu is 0.4, r is 0.8 g, so that gives us a friction of 0.32 g. We need to take that away from 1.6 to find out how much we have at the end. Let's have a look at the end setup here. Our gravitational potential energy is still 0. The kinetic energy is 0 because it comes to rest. The elastic potential energy is lambda times x squared over 2 times L. So that's 2 times 0.5, which is 1. 10 divided by 1 is 10, so we get 10x squared there. And the total, this is the key part in this question that's different from the previous examples, the total is 1.6 minus friction times the distance travelled. So the total is 1.6 minus 0.32 gx. This is our external force, work being done against friction. So our total here, 0 plus 0 plus 10x squared, must equal this reduced amount of energy. That gives us our equation. 10x squared must equal 1.6 minus 0.32 times 9.8x. And again, just for the sake of time in the video here, I will do that on my calculator, which gives me the answer of 0.272 ... or minus 0.586 ... Similar justification to the previous one, because we start with no extension or compression and we're being projected this way, the first time we come to rest must be a positive extension, not a negative, even though, because it's a spring, the negative might be possible, although in this case, with a natural length of 0.5, you can't have a compression greater than that. So for a couple of reasons, we can discard this one, and the extension must be 0.272 ... And the extension is also the distance moved, so this is our final answer, and because I've used g, I will round this to 2 significant figures. That's it for the textbook questions. Now for a few exam questions. A light spring of natural length L has one end attached to a fixed point A. Particle P of mass m is attached to the other end. The particle is moving vertically. As it passes through the point B below A, where AB is L, the natural length, its speed is this. The particle comes to instantaneous rest at point C, 4L below A. This speed here is giving you a clue to use energy, not forces. So let's sketch this out. We've got a spring, natural length L, attached at point A. At the start it is moving and it passes through point B, so I'll draw it through point B, but it's moving downwards with a speed root 2g capital L, and the distance here is capital L, which is also the natural length of the spring. It moves downwards, going beyond its natural length, so it extends out and gets all the way down to 4L down here, where it comes to instantaneous rest. And that's point C, and this distance is 4L, so the extension at this point we already know is 3L, where the extension here was 0 because L is the natural length of the spring. So at point B, we've got gravitational potential energy. If I use A as my 0 level, that is mass times G times H, which in this case is minus L. We've also got kinetic energy, which is a half times the mass times V squared, which is nice, that's the square root, so that becomes 2GL. Half and the 2 cancel out. And our elastic potential energy at this point is 0 because there's no compression or extension. So our total energy in the system at B is equal to 0 because we've got mgl minus mgl. At C then, we also need a total energy of 0 because no external forces are acting. Gravitational potential energy is equal to mass times gravity times minus 4L. Kinetic energy is equal to 0, and the elastic potential energy is equal to lambda times x squared. We know x this time, 3L, divided by 2 times the natural length L. For a total of 0, we just need to sum these two together. So this plus this equals 0. Our equation then, minus 4Lmg plus lambda times 9L squared over 2L equals 0. That cancels with that, and we get 9L lambda over 2 is equal to 4Lmg. L's cancel, take the 2 over, we get 8mg is equal to 9 lambda, so lambda is equal to 8mg over 9 as required in the question. Exam question number 2. A light elastic string has natural length 2L and modulus of elasticity 4mg. One end of the string is attached to a fixed point A, the other at B, where AB lie on a smooth horizontal table with AB equals 4L, 2 times the natural length of the string. A particle of mass m is attached to the midpoint of the string. So if I set this up, we've got A over here. String is stretched between the 2 points A and B. This is a distance of 4L, and we know lambda is equal to 4mg. A particle is attached to the midpoint, but it doesn't stay there. The particle is released from rest at the point of the line AB, which is 5L over 3 from B. That's a little bit less than 2L, so it has been pulled slightly closer to B than A. So if I get rid of that and move it over here slightly, so this distance is 5L over 3. This distance then is 7L over 3. And initially it's released from rest, so at this point v is equal to 0. The speed of p at the midpoint of AB is v. So it's held here, it's released, and it goes this way. And as it passes through the midpoint here, the speed is v. So in yellow here, little v is equal to capital V. Okay, take a moment here and think about what's going on. We've got the particle here, and although it's one long string, it's going to be much easier, I think, to consider this as 2 separate strings. So if we consider it to be one string on the left here of length L, and the other one on the right here also of length L because it was attached at the midpoint, then the string here is stretched a little bit to make it 5L over 3, so the extension is 2/3 of L. And the string over here is stretched more. It's stretched 4L over 3 to make a total of 7L over 3. So the string here is stretched more than this one is, so it has a greater tension, which means when it's released from rest here, it moves this way. And that makes sense given what we've been told about the midpoint speed being v. So putting all of the energy in, we've got at the start GPE equals 0 because it's all happening on a horizontal level. Kinetic energy equals 0 because it was released from rest. And the elastic potential energy in my imaginary 2 strings instead of one long string is going to be this and this. So we've got lambda 4mg times x. So I'll do this one here first. So half of the original string, the natural length was L, and it's been extended to 7L over 3, so the extension is 4L over 3. We need to square that and divide it all by 2 times the natural length, which for this left-hand half of the string is L. But we've still got elastic potential energy on the other side if we consider this little piece here, because this is also stretched from L to 5L over 3. It's all really one long string though, so lambda is the same. 4mg times the extension on this side is 2L over 3 squared, divided by 2 times the natural length of this half, L. At the end, we've got GPE still equals 0, kinetic energy is equal to a half times the mass of the particle, m, times v squared, and we've just been told it's capital V. And the elastic potential energy is very similar to this. We've got 2 halves that I'm considering of the string, but because at this point we're looking at the midpoint, they will be the same. The extension on this side will be L, and the extension on this side will be L. So we'll have the same expression twice. 4mg for lambda, L for the extension, over 2 times L, plus 4mg, L for the extension on the right half, 2L. So we can simplify that quite easily. That cancels. So does that, and then they add together to give me a fairly straightforward 4mgl. Now I haven't written the total part, but we know that the total here must equal the total here because no work has been done to put energy in or take energy out of the system. So 0 plus 0 plus this must equal 0 plus this plus this. But before I do that, I'll just tidy this expression here up, because we can cancel here. And in here, I've got 16L squared over 9. Here, 4L squared over 9. So that's 32 mgl over 9 plus 8 mgl over 9 is 40 mgl over 9 for the simplified expression there. So the energy at the start, 0 plus 0 plus 40 mgl over 9 must equal the energy at the end, 0 plus a half mv squared plus 4 mgl. All of the m's cancel, and we can rearrange to get v squared is equal to 8 over 9 gl. Then when we square root that gives us 2 root 2gl over 3. So we get 2/3 root 2gl. All of that is a fairly large part A. Part B is much smaller. Explain why v is the maximum speed of p. Okay, I won't write this out like I normally don't, but I'll talk it through. For this, we're going to go back to forces. When we pull this out here, initially, we've got a tension on both sides. But the tension on the left is greater, and that's why it moves this direction when it's released. In the middle, although there is still tension on both sides, because A to B is 2 times the natural length of the string, the tension either side of this point is equal and opposite. That's important because that's our equilibrium point where the resultant force is 0. And if the resultant force is 0, then the acceleration is 0, and maximum or minimum velocity occurs when acceleration is 0. So this is the key point to focus around for this question. V is the maximum speed of p because it is happening at the midpoint, and at the midpoint the tension in the two strings is equal and opposite, therefore A is 0. Maximum speed occurs when A is 0. Third and final exam question. A light elastic string has natural length 4 meters, lambda this, particle of mass this is attached to one end of the string. The other end is attached to a vertical point A, is released from rest at A and falls vertically. So we've got A here, and the particle is released from here and it falls. Find the distance travelled by P before it immediately comes to instantaneous rest for the first time. So this is very similar to what we had in one of the examples from the textbook. It's falling down to here, where the distance between here and here is the natural length 4 plus the extension. And at this point it has velocity 0 because it comes to instantaneous rest. It also starts at rest here, and because it's a string, not a spring, there's no compression. There is going to be gravitational potential energy, so I'll put h equals 0 at this point as well. The particle is called P, so I'll call that point P. At A, the energy considerations, gravitational potential energy is 0, the kinetic energy is 0, and the elastic potential energy is 0. So the total is 0. At P, the gravitational potential energy is equal to mass, 0.5, times 9.8, times the height, which will be minus 4 plus x. The kinetic energy will be 0. The elastic potential energy will be lambda, 58.8, times x squared, divided by 2 times the natural length, which is 4. And that total must also be 0 because there are no external forces. Our equation then is minus 19.6 minus 4.9x plus 58.8 over 8, 7.35x squared, and all of that has to equal 0. Solving that gives me 2 and minus 4 over 3. Remember, in an exam you should show the method of solving a quadratic equation. In this case we have a string, not a spring, so I can discard the negative answer. So the extension is 2, but the question is find the distance travelled, so it's all the way from here down to here, 4 plus 2. So the distance AP is equal to the natural length plus the extension, 4 plus 2, 6 meters is how far it has travelled. Part B, the particle is now held at a point 7 meters vertically below A and released from rest. So at 7 meters with L is equal to 4, that gives us an extension of 3 meters. It's released from rest, so the velocity is 0. Find the speed of the particle when the string first becomes slack. Now it becomes slack when the extension is equal to 0, and that will be at 4 meters below A, the natural length of the string. This is actually quite a different question, so I'm going to clear all this off and start again. So we've got our point A here, and the particle is being held all the way down here at a distance of 7 meters. If I use h equals 0 here, perhaps I should call that minus 7, put an arrow on. It's released from rest, and then when it first becomes slack, that's here at a distance of 4, so a displacement of minus 4. And we're trying to find the speed, v. Same idea as before. Our starting energy, we have gravitational potential energy of mass 0.5 times 9.8 times minus 7, which is minus 34.3. We have starting kinetic energy of 0 and quite a lot of elastic potential energy. Lambda times the extension squared divided by 2 times the natural length, 66.15. So the total energy is 31.85 joules. At the end, we have gravitational potential energy, mass, times 9.8 times minus 4, which is minus 19.6. Kinetic energy, a half times the mass times the speed squared. And the elastic potential energy when the string becomes slack is 0. Total here, minus 19.6 plus v squared over 4. Again, as we form our equation, there's no energy being added or subtracted from the system, so it's just this must equal this. 31.85 is equal to minus 19.6 plus v squared over 4. Solving for v gives a final answer of 14.345 ... but because we've used g, the two significant figures, 14 meters per second. And there we go. Quite a long video, lots of examples, a few exam questions. I hope that's enough for you to have a go at the questions in exercise 2D and the chapter 2 review exercise, and maybe I'll see you for chapter 3.